Welcome to the next lecture in the BIM Basic series. Last time I presented basic information concepts related to BIM. Today we will talk about creating an object-oriented BIM model with its multidimensionality and level of detail. We will start by discussing computer graphics, mapping and building design documentations, projections, of course, from the point of view of the BIM methodology. Next, we will look at the BIM model as an information container, together with objects and relations between them, of course. I will present the multidimensionality and levels of detail of BIM models.
We start with a computer graphics. In vector graphics, an image is drawn with line segments or arcs, drawing primitives such as lines, polylines, arcs, and 3D objects such as basic cubes or spheres can be used. Mathematical equations are used to create primitives. In the past, an image was created in this way on plotters, and until 1980s, CRT monitors were used to draw the image in the same way as oscilloscopes. Raster graphics. It is an image which is made of rectangular grid, like a matrix, of closely spaced dots, so-called pixels. The main parameter, in the case of raster graphics, is the bitmap size in pixels, usually given as a rectangle's dimensions. In fact, it can be said that the first examples of raster graphics were the paintings of Impressionists. The most important file formats are BMP, JPG, TIFF, PNG, or GIF. And the most important graphics editors includes MS Paint, Photoshop, or GMP. Actually, we'll not deal with raster graphics anymore unless we need to integrate our vector or virtual objects with a raster. It can be a wall surface texture or a background from a photo showing the design object's real surroundings. However, this is rather the domain of architects. Actually, we'll only discuss vector graphics now. Its description is based solely on mathematical formulas and vector coordinates. It is mainly used to create technical drawings. So-called primitives are used, which can also be objects such as lines, polylines, polygons, circles, or ellipses, Bezier curves, texts even. But they can also be special primitives in surfaces, a way of surfaces and solids, such as cubes and spheres. The most important file formats are DWG, DGN, CDR, PDF, and the most important graphic editors are AutoCAD, MicroStation, CorelDRAW, and SketchUp. The main advantages of vector graphics are scalability and simplicity of description. This is due to a mathematical description that is independent of magnification and display. Image modification is straightforward. It is enough to change its parameters. This can be, for example, a different line and coordinates or a different radius of the circle. Thanks to this, the graphics take a smaller size. I mean, the amount of memory. Of course, in the non-photorealistic applications. We use it to create diagrams, technical drawings, logos, flags, and charts. It is also worth mentioning that vector graphics allow us to use plotter following their work method. It also has an excellent conversion to raster graphics. Importantly, these graphics allow us to describe three-dimensional space, which actually cannot be done in raster graphics. Voxels are an attempt at a quasi-raster description of three-dimensional objects. You probably know them from Minecraft, although you probably call them cubes there. Voxel is the smallest element of space in three-dimensional graphics. In a way, this is the equivalent of a pixel in 2D graphics. Using voxels, we describe, we describe space as a three-dimensional matrix whose individual cells have specific sizes. Graphics based on voxels can most often be seen on images obtained from various types of tomographic devices. However, not everything is possible with vector graphics. First of all, it is about presenting photorealistic images. The mathematical description of such images using vector-based formulas is very complex. It is also not profitable to vectorize such complex raster images. Therefore, it works best with a small amount of detail. We will definitely not use it when we want to preserve the photorealism found in images and photos. The process of converting a raster image into a vector image is called vectorization or digitization. However, please do not confuse the simple scanning of a paper map with its vectorization. For this, we need to use special algorithms that analyze the scanned raster or devices such as digitizer or tablets when vectorization is done manually. We'll now focus on a mapping representing spatial objects in the form of flat or three-dimensional models. In the case of planes, projections, these will be isometric drawings and orthogonal projections. The three-dimensional representation can be represented by wireframe models that appear to be made of wire. Wall models that already have their edges obscured by model faces but are empty inside. And finally, we have solid models that have already filled interiors and we can mark the edges of interpretation on them. It is the solid models that give us the greatest opportunities and are used in BIM tools. They allow the creation of new solid by logical operations, otherwise known as Boolean operations. It is about determining the intersection, sum, and difference of two solids. In this way, it is possible to create more complex solids from primitives. Interestingly, these solids remember the history, making them easy to edit. Having a solid model, you can almost automatically generate a 2D drawing in projections or sections of the solid model. You can also come across the concept of object-oriented graphics. This is the case with models created in BIM tools. These are complex graphical objects supplemented with non-graphical information that may affect the graphical representation's appearance and behavior. By changing, for example, the property of the object in the form of the degree of transparency of the material, you will affect the final image obtained. Objects can also be related to and dependent on neighboring objects. Changing one of them may affect others. For example, a change in the slab position, the sailing position, will cause the change in the height of walls or columns associated with the sailing. The same will happen when you move the wall containing the window. It will move with the wall, which was not possible in CAD programs. In this way, a building model is created, which is actually a kind of database describing individual components and their relationships. Relationships are hierarchical and can be viewed and modified. Here we see a model of the building that you can create during the lab classes. On the right, I've shown a list of objects that make up this model. So we can see types such as columns, walls, slabs, benches, stairs, doors, windows, etc. We can indicate an object on the list or the model and see its properties on the list with parameters. Importantly, these properties are not only graphic, but also describe the material, price, installation time, and even the damage found during inspection, for example. Unless, of course, the tool allows us to add such data. Let's see now what the representation of the building looks like. In a construction drawing, a structural drawing, we most often use orthogonal projection. It allows us to present three-dimensional objects in two dimensions. It is a form of parallel projection where the view direction is perpendicular to the projection plane. There are flat projections and axonometric projections. Plans, sections, and elevations views are the most common types of plan views in building design practice. An axonometric projection shows an object's image at an angle to reveal more than one side of the same image. Axonometric views are often used by interior and furniture designers. In turn, the perspective view shows three-dimensional objects on a flat surface as the eye perceives them. Architects often create photorealistic perspective views outside and inside a building to help building owners understand the design concept. Axonometry is a type of parallel projection. It is used to map space to plane using a rectangular axis system. The feature that distinguishes axonometry from other types of parallel projection is the striving to maintain the real dimensions of the projected objects in at least one selected direction. Axonometry is widely used in engineering drawing. Axonometry is divided according to the direction of the projected axis of a rectangular system. It could be isometry, when all axes of rectangular system in space form the same angle with the viewport and their images are subject to the same abbreviation. The viewport shows an image of three axes forming angles between each other at 120 degrees. Then we have diametry, when two of the axes of a rectangular system form the same angles with the viewport, and therefore the coordinate system has the same abbreviation on at least two axes. And finally, we have trimetry, when each axis of a rectangular system forms a different angle with a viewport and is subject to a different abbreviation. In the case of perspective views, depending on the viewport's position, in relation to the main object in the image, we speak of a 1-point, 2-point, and 3-point perspective. There are three axis directions related to the object, somehow related to the object. The most obvious connections is when the object is cuboid. We get the individual cases by selecting the viewports so that one, two, or three of these directions are not parallel to the viewport. The essence of perspective is the projection of all points in space onto a plane or other surfaces, relative to some point called the center of perspective. This presentation creates an image in which, apart from certain specific situations, the real dimensions and angles in space are not kept apart from certain specific situations. The image is deformed. It is characteristic that the presented elements shrink as they move away from the point of observation. Lines parallel to each other in perspective converge and meet at some theoretical point. The construction of perspective in a drawing and painting is based on the so-called vanishing points that allow you to determine the correct shape of the presented object. Perspective is the most commonly used and natural way for humans to map space on a flat surface. Having a three-dimensional and solid building model, we can automatically generate its views, projections, and sections. At the same time, we list certain types of mapping specified in the construction drawing. First, the floor or floor plans. They are a bit like maps that also have a top-down projection. But unlike a conventional map, a floor plan is usually a section formed by a horizontal plane roughly halfway between the floors. Objects below this level are visible, and objects on this level are shown as cut. Usually, we draw them with thicker lines or we use hatching. Objects above the cut plane are omitted or displayed as dashed. Floor plans are the basic parts of any architectural and construction documentation. The construction works are mainly based on these drawings. There are many types of these projections and various drawing elements are placed on them. They can be distinguished by discipline, scale, or stage of the project. We can see the most common elements here. The content of views can vary widely, but the main structural features are always displayed with the appropriate dimensions and annotations. Non-structural elements such as fixed or movable furniture can also be shown, especially in architectural drawings. The vertical sections are also a perpendicular projection of three-dimensional object but formed by a building's intersection with a vertical plane passing through the object. In such views, the object's part in front of the plane is omitted to reveal what lies beyond the plane. As with floor plans, we can distinguish between the content, scale, and phases of a project. Sections are needed to define the vertical position of the building elementary clearly. Such information is difficult to show in the floor plan drawings. The elevations of each floor level help designers measure the vertical distances between building elements. An elevation is a perpendicular view of a three-dimensional object from the horizontal plane next to the object. In other words, the facade is the view that the observer looking at the structure from the front, back, left, or right has. An elevation is a common method of representing the external appearance and a detailed description of a three-dimensional object in two dimensions. The facades are the most common orthogonal projections showing the appearance of the building from the outside. The facades can be shaded and colored to make it easier to identify materials used on the building's exterior surfaces. Besides, architects can add material descriptions to the facade drawings with a color and material codes. Another problem is the visualization of the building model. The possibilities depend, of course, on the tool and our disposal. However, most programs allow you to hide or sharpen the edges of solids, shading and covering with texture, turning on transparency, and this is on the entire model or selected objects. Visualization are rather the domain of architects, especially if we are talking about photorealistic images. We can use them to analyze lighting, simulate the interior's functionality, evaluate the integration of the designed building with the existing surroundings, and create bird's eye views. They are also used in the form of interactive models in virtual reality. Now let's see how BIM models can become part of the building's design documentation. Basically, the design documentation of a building consists of a drawing and a cardboard part. The drawing elements include maps, the layouts shown a moment ago, sections, elevations, interior views, and details. These will be technical descriptions, calculations, schedules, bills of quantities, and cost estimates, specifications, agreements, and opinions in the text part. Therefore, a BIM model can also contain different types of objects. They also divide it into graphic and non-graphic. From the graphics, you can generate drawings documentation in the form of projections, sections, and elevations. Technical descriptions, schedules, bills of quantities, cost estimates, and specifications can be generated from non-graphics information. Can also be used in calculations. This non-graphical part in BIM is now particularly strongly developed. Models can store more and more different types of information. If a tool doesn't yet use this data, it can usually save and share it. In this way, other applications and plugins of a narrower and more specialized nature take advantage of them. In this way, we have come to the conclusion that the B model is actually a container of information. BIM is actually a way of modeling information about building. Under this concept, designers can use 3D building models to produce all required project drawings, such as plans, sections, elevations, visualizations, and construction details, as well as bill of quantities and cost estimates. Therefore, changes to the model are immediately updated in all drawings. The model is related to non-graphical information. It even allows us to simulate buildings, staging processes, or operating scenarios. The virtual building model contains the complete building model and all its representations. Documentation progress automatically flows between model elements. Model changes affect all drawings and vice versa. Building elements from the component library provided by manufacturers are used for modeling. Non-graphic data is attached to graphic object. BIM modeling software with tools for immediate model visualizations. It is also possible to simulate and view the schedule or costs. Library components used for modeling have their realistic representations. Each three-dimensional component has its own views, projections, sections, color, and texture. It can be described parametrically, which allows you to change its dimensions, fill, and background. It can also be linked hierarchically with other components, so changing one will affect the others. They also relate to non-graphical information in the form of material description, properties, quantities, costs, and specifications. The finite element model, analytical model, can also be associated with the BIM model. In many BIM programs tools, the analytical model is created simultaneously with a three-dimensional basic physical time model. Usually, however, the simplified form of the model hides non-structural elements. For example, an architect or installation engineers, facility engineers, cannot see them because they do not need them. The analytical model can be exported to calculation programs, analyzing programs, where static or dynamic analysis and dimensioning of structural elements and connections details are performed. The connection of bar elements, such as columns and beams, takes place automatically. Bar connections at nodes are detected. If the distance is too great, it may cause separation, and then a manual adjustment is needed. The same is true for surfaces, elements such as walls, slabs, and foundations. Small inconsistencies also require a manual adjustment. And now a few words about the types of objects in the BIM model and the relationship between them. From CAD techniques, you probably remember more complex objects which were blocks. They were used to draw components repeating in the drawing. They were taken from previously created block libraries. However, they were, as a rule, static and limited to a specific view. They also had limited storage options for non-graphical data. Over time, dynamic CAD blocks and the ability to define attributes for saving text data were created. It was not enough, however. This was because the blocks were actually a collection of related CAD drawing primitives. BIM methodology changed everything. Together with it, the concept of a family was introduced. Therefore, we distinguish systemic and non-systemic families. Systemic families are objects with a specific function in the model, and they are a component element of the modeled structure. For example, column, beam, wall. They are saved in separate files and available directly in the master model creation environment. You do not need to use the family editor to create them. Non-systemic families are one or more elements combined into one object. The layout of elements is created and edited in the family editor. After being inserted into the model, it is properly oriented in relation to other objects and establishes relations with them. It is also often parameterized. The idea here is similar to dynamic blocks in the AutoCAD environment. Now there will be some examples of systemic blocks. First, columns. Here's an example of a steel column. You can select the column cross-section and material from the list. Since it is a construction element, structural element, we can also manage its analytical representation. Here are examples of rectangular concrete columns. After choosing the type, we can change the parameters such as height and cross-section. Each type can be duplicated to create a new type from it. It inherits the traits from his ancestor. This is the object-oriented modeling approach. Beams are another example of the system family. These are also design elements. They can be horizontal or diagonal. They also have their own analytical representation. Additionally, it is possible to create patterns of beams, making it very easy to build more complex models. The properties of the beams depend on the type of beam. It will be different in the family of steel beams and different in the case of concrete beams. The next system family is walls. There are load-bearing walls represented in the analytical model and architectural walls that are partition areas without representation in the analytical model. Additionally, we can define wall details in the form of cornices and rustication. The last example of systemic families that I'd like to show today are slabs. Here, too, we distinguish construction and architectural slabs. Uh, in the case of non-systemic families, we use the family editor, in which we define our own family by parameterizing its shape and dimensions. Here we have it shown on the example of a column cross-section. When creating families, we can use parameters determined by formulas that use different parameters in the calculations. Formulas can perform standard operations, conditional statements, functions, and various units. When creating a family, we also define the material by providing general information with its name and description and its appearance, which can be graphically represented differently on the surfaces. Besides, we determine physical and mechanical properties such as strength, thermal expansion coefficient, and thermal and humidity properties. The material assigned to the outer surface layer influences the visual appearance of the element. It's all about color, texture, and hatching. I already spoke about multidimensionality in the last lecture, but now we will see more examples. So just to remind you, 3D is only geometry. 4D is about time and schedules. 5D is the cost. 6D, durability and environmental analysis. Whereas 7D is about facility management. We start with a 3D. The three-dimensional model allows us to almost automatically create paper documentation in the form of sections, projections, and elevations. We can also create a workshop and reinforcement drawings and details. It is actually possible to visualize the object in real time, and we can take virtual walks on it. This allows us to introduce construction phases and improve the functionality of the target planned structure. We can create photorealistic images and animations, also for marketing purposes, but above all to detect various collisions like geometric, construction, interdisciplines. Model visualizations can be of different nature. It all depends on what objects we are dealing with. We need different information when visualizing a new building and elements of urban infrastructure, and different when analyzing the lighting of the room and the functionality of its equipment and furniture. Now there will be some examples of 3D models for structural elements created by various BIM tools. First, steel structures in Autodesk Revit. Trimble Tekla structures is a very efficient tool for structural engineers. Here we see examples of steel element connections. In the Autodesk product group for modeling advanced steel structures. Tekla is able to integrate models of steel and reinforced concrete structure. Here's an example of a complex structure. Products from the Nemetschek group have great opportunities. Here we have Allplan for modeling reinforced concrete structure. Reinforced concrete structures can also be created quite efficiently in Autodesk Revit. Tekla also has components for modeling pre-stressed or post-tension structures. But construction or BIM is not only steel or concrete structures, it is also the design of roads and railroads. Here's an example of open roads by Bentley Systems. Autodesk offers a group of collaborative infrastructure design products. Pre-design takes place in InfraWorks. The program also includes models of simple bridges. The detailed design of the road or railway is already carried out in the Autodesk Civil 3D program. Trimble, on the other hand, proposes the Quadri program in this regard. And now the 3D dimension, which is used for construction planning and management. We can develop logistics for the supply of materials and services. Here we prepare the development of the construction site with the fence machines, cranes, traffic organization, and occupational health and safety. The schedule can be illustrated with an animation that allows you to analyze the dependencies and of the processes and look for a critical path. One of the best products in this dimension is Bentley Synchro. The schedule can be visualized on a time-changing model. It can also be presented in a dynamic way of animation. A time-changing model can be linked to a dynamically changing schedule. We can observe a moving line on the timeline and changes in the model. We can plan the location of all machinery and equipment on the construction site. We can check collisions and perform constraints and risks analysis during construction within changing conditions. The 5D dimension includes takeoffs that can be linked to a changing model and cost estimates. We can create scenarios and financial montages for the entire investment. We can compare the assumed and actual costs during construction. Very often, this product group works independently outside the main BIM environment or in the form of plugins. This is the Polish Norma program that reads the model in the open IFC format. Similarly, different Polish BIM Estimate program of the Krakow company Datacomp works. The 6D dimension is an element of the philosophy of sustainable development. We can estimate and optimize the cost of use and energy consumption, plan repairs, modernizations, and demolitions. Our proprietary models or plugins allow the use of data and tools for lifecycle assessment analysis. Here we have an example of an analysis of the energy demand of a building. Here in turn, a program to determine the carbon footprint of the building. The 7D dimension is a tool for managing an existing and used facility during operation. The designer model is updated during construction and then in use in operation time. We collect information about all the damages, repairs, and modifications. There are instructions and operating procedures associated with the model. There are two types of products in this area. Building facility management, used mainly for cubature facilities, buildings, and infrastructure asset management, for example, management of infrastructure facilities such as roads, railways, and bridges. First, building facility management. This is actually a typical real estate economy. Often, such services are used by housing communities or tenants or owners of premises in apartment buildings. With these tools, we can provide the best level of service. Building management and maintenance costs can be reduced. Improve, you can improve security and protection. Record inspection results, assist cleaning, plan adaptation and repairs. Infrastructure asset management, on the other hand, is the tool for managing infrastructure assets. That is, roads, railways, bridges, and all water, sewage, heat, and energy networks. This approach covers the entire life cycle of managed assets. It takes into account repetitive processes such as design, construction, commissioning, operation, maintenance, repair, and then modification, replacement, and disposal of the assets. The last issue to be discussed today are the levels of detail of the BIM model. In a classic investment process, at the various stages of its implementation, a different level of detail of project documentation is used, design documentation. Such documentation, drawings, descriptions, specifications, looks different at the concept stage, different in the construction and workshop design, and still different in as-built drawings. In the case of BIM methodology, variable levels of detail of BIM models are also used. They are well defined and illustrated by examples. They guarantee at each stage of the project implementation a sufficient minimum amount of information in BIM models, which is necessary for the evaluation and approval of the proposed solutions by the contracting authority. Thanks to this, it can be done without the design and executive teams incurring an excessive workload related to unnecessarily detailed modeling at a given stage. This approach is consistent with the idea of lean construction. It allows us to eliminate losses resulting from too much information saturation. There are two ways of describing the details of models in the world. In the United States, the term LOD is used, it is abbreviation to a level of development. And examples like LOD 100, LOD 200, etc. It was originally developed by American Institute of Architects and is currently being developed by the BIM Forum. The American LOD is a classification that describes what a BIM model should look like at the next stages of the construction processes. It determines the level of detail in the graphics of model object and the non-graphical information attached to them in the form of attributes. They are called metadata. In the UK, on the other hand, another newer LOD standard, abbreviated to level of detail, has been adopted, and examples LOD1, LOD2, etc. It was developed by a BIM task group and the British Standards Institution, and it is described in the British Standard PAS 1192. This classification applies only to graphic data and is used to describe the minimum level of detail in the graphics of modeled 3D objects. The level of detail of non-graphical information is determined by an independent LOI classification abbreviated to level of information. For example, LOI 1, LOI 2, etc. As I said, the American standard is being developed today by the BIM Forum. So every year, this organization publishes catalogs that illustrate how to model individual building elements at different levels of detail. The British standard is presented in the form of such a table with graphic examples. Since in the British standard the level of detail of the graphic LOD may be independent of the level of detail of information LOI, the concept of level of model definition LOMD has been introduced. Of course, it is not an algebraic sum of both levels, but rather a joint representation of both kinds of information. The BIM standard PL also provides a proposal for classifying the levels of detail of BIM models. It uses levels of detail in the line with a UK approach. It is more similar. It also treats LOD and LOI independently, but the number of levels is reduced to 5 levels that match the next stages of project documentation in Poland. That is the concept: construction design, detail design, construction commissioning, as well as final acceptance. This is how the table of levels look like in BIM Standard PL, showing examples of modeling columns and stairs. Virtually every country introduces its own level of detail classifications. Unfortunately, they are not yet consistent with each other. Here I try to show these differences using the example of 4 national systems: British, American, Italian, and Polish. You can see that the Italian system has the most levels. There are 8 of them, and they are marked with letters from A to G. The British one has 7 from 1 to 7. The American one has 6 from 100 to 500. And the Polish only has 5. In this table, divided into 3 slides, I've compiled the 2 most commonly used systems globally, the American and the British, but concerning the design stages used in our country. A proposal for detailing geometric data and non-graphical information was given for each level, first level 100 or 1 and 2 in British. Here we have the continuation of this table with levels 300 and 400, or 4 and 5. And the last part with levels 500 or 6 and 7 UK.
This ends today's lecture. It started with a discussion of computer graphics, mapping, projections, and designing documentation of the building. It was done from the point of view of the BIM methodology. We looked at the BIM models as an information containers, together with their objects and relations between them in virtual reality. I also presented the multidimensionality and detail of level of details in of BIM models. Thank you very much for your attention, and I invite you to the next lectures in the BIM Basic series.